Grade 11s, welcome to this session. We're going to be looking at light calculations today. So make sure you have all your facts and things at your fingertips, because we're going to be applying what we've learnt about light. And let's have a look at the detail that we're needing to go into. So come with me and let's have a look. We're focusing on light calculations, and in particular we're going to do two very important big ideas. The first thing is we're going to use the relationships that exist between frequency, wavelength and speed in light calculations. Now, although this might sound really silly and quite easy, you do need to revise this, and some of the calculations could be a little bit difficult. So we want to give you some examples of those, remind you about what to take note of, and then we'll move on to the second part, where we're going to focus on Snell's law. And we're going to use Snell's law to calculate the speed of light through various media. That's different materials. We're going to use it to calculate the angle of refraction, the critical angle, and the refractive index of various things. Now, this session is a build on from our previous session where we investigated and we looked at all the different amazing properties of light. You need to make sure that you've gone over those and that you're familiar with everything. We will try and just do a little bit of revision now and again, but the main focus is on solving some problems, looking at the different types of examples that you can be given, and let's see if we can solve them. So let's kick off straight away by just reviewing very quickly the relationship that exists between light and different physical properties. So terminology and relationships is where we're at. And the first thing we're going to come to, and it's probably the most important constant around, the speed of light is a constant in a vacuum. And that value is given a symbol c, and it's 3 times 10 to the 8 meters per second. Now, you need to know that. It's not given in questions, so you can assume that where they talk about the speed of light, that you must use 3 times 10 to the 8 meters per second. Now, remember that in air, the speed of light is about the same. In air, it's very close to 3 times 10 to the 8 meters per second. We can approximate it and say, in air, we'll take it like that. But in other materials, light slows down because light undergoes the process of refraction when moving from different materials, and so the speed of light will change. We need to be aware of that. Okay? Next thing that you need to be aware of is that there's this idea of frequency. Now, frequency has a symbol F. For any wave, we use the symbol F, and we recognize that it's measured in hertz. So the frequency of light tells us how many oscillations or complete cycles there are per second. And we recognize that light is produced because of electromagnetic radiation. The source of electromagnetic radiation is an accelerating charged object, and that frequency, that movement of cycles moving up and down, will influence the frequency of the light that's produced. Visible light has a band of frequencies. We need to recognize that band of frequencies. It forms part of the electromagnetic spectrum. We go from red light all the way to violet light in increasing frequency. So the lowest frequency would be red, and the highest frequency of visible light would be violet light. Now, the wavelength, given a symbol lambda, and it's measured in meters. And again, what we need to recognize is the relationship between these two. Because the speed of light is constant, we recognize that the frequency is inversely proportional. That means it's proportional to 1 over lambda. It's inversely proportional. Inversely proportional. That means that if you have a high frequency for a certain wavelength of, or type of light, color of light, that means there will be a low wavelength. Okay? they work opposite each other. As you increase the one, you will decrease the other. And so you need to be very clear about that. How do we relate that in a formula? Well, remember that we can say the speed of light, the speed of any wave, is equal to the frequency times the wavelength. And there you can see these two variables are multiplied together to give you a constant. This is a constant. So it's a very good example of an inverse proportion. Now, please remember, though, that when we're talking about speed and distance and time, we can relate speed to that as well. So where we spoke about the speed of light as being c, we need to recognize that v, the velocity or the speed of something, is also equal to the change in displacement or distance, the change in position, divided by the change in time. So be very clear about exactly where you are when you're doing calculations with speed. You can either use the relationship between frequency and wavelength to find speed or to find wavelength or so on, but you can also use the change in position and the time that's taken. So that summarizes for us the relationships. Now let's move on and let's take a look at a question. Now, this is an interesting question, and we're going to go through it as if we were going through an exam question. It says, a laser light is used to produce a series of short flashes of light. So first of all, we recognize that we've got a laser. Laser just means that it's of one frequency, nothing more than that, and it's got a series of flashes. No real critical information up until this point, but let's move on. The light has a frequency of 4,40 times 10 to the 14 hertz. So that's a fairly low frequency when it comes to light. Lasers can have much higher frequencies of the order of 8 times 10 to the 14. But the lasers that we're looking at here are on the lower end of the spectrum, probably a red sort of colored spectrum, although that's not required. So what are we told? It is reflected off a mirror on a satellite positioned directly above the laser. Now, the time taken from the moment the signal is sent to the moment that the reflected beam is detected is 0,24 seconds. So here's our scenario. We're on Earth, and we've got this little laser that it pulses. So we can tell the different lengths of pulses to identify a particular pulse. So the pulse might be for 2 seconds, and another pulse might be for 3 seconds, and another one for 4 seconds, and then start with the 2-second pulse again. And that way we're able to measure where the pulse has been emitted, time from the moment it was emitted to the moment that it was detected. We're told that this is going vertically up to a mirror on a satellite that's in geostationary orbit above the Earth, and it's going straight up and it's coming straight down. A detector is picking it up. Now, interesting idea. We use this to measure distances, to calibrate all sorts of things, but here is the test. We're going to now ask the question, how high above the Earth is the satellite orbiting the Earth? So we're wanting to work out a distance. We're wanting to recognize that the light beam has traveled from Earth up to the satellite. It's been reflected back down again. Before we carry on and do that calculation, let's just make sure we've got the other parts to the question sorted and that we can be thinking about them. So then it says, what is the wavelength of the light emitted? And the next one, if a different high-frequency laser was used, would there be a difference in time? That's an interesting idea. Perhaps we can explore that a little later as we come to it. And then the thing, if you needed a slightly longer time to measure the difference in signals, what could you do? Okay, so when you're given an exam question, it's really important, don't just read part A, because it might be that part B, C, and D give you some ideas of how to answer A. you might want to also list the information that you've given, and so that you can see very clearly what you've got. So what we know so far is that we've got frequency over there, that's the frequency, and we've got a time, the time equal to 0.4 seconds. So first question is how high? We're asked to find the distance. We recognize that for part A, I like to draw a little sketch. So I'm going to say, here's my little laser beam, and here's my mirror sitting on the satellite. What we recognize is that the beam is going to go straight up, and it's going to come straight down. It's going vertically up, and it's coming directly down, and we can measure the difference in time. Hope you've got that. So we recognize that the time for the signal is 0.24 seconds. What else do we know? Well, as I mentioned to you earlier, we know that the speed of light will travel at 3 times 10 to the 8 meters per second. Now we want to find distance, so I'm going to write down the formula. Speed equals distance divided by time. There are other forms of that, but let's just use that. We're going to isolate and find this missing quantity here. So the way I do it is I always like to write the formula down and then substitute in. So I'm going to substitute 3 times 10 to the 8 meters per second. I'm going to say I want to find the distance, and I know what the time was. The time was 0.24 seconds. So now if I want to get distance on its own, get my marks for substitution. I can say that distance is equal to the speed, 3 times 10 to the 8 meters per second, multiplied by the time, 0.24 seconds. So let's put that onto the calculator and let's work it out. So we get 3 exponent, 3 times 10 to the 8, multiplied by 0.24. And that gives me a really big number of 7, let's just see exactly what it is. If I change the 702 or 7 million or something like that meters, I just want to change it to scientific notation, and you can see there it's 72 million meters. Notice that I've kept my units for speed as meters per second, so this must be in meters, 72 million meters. But I need to just write that a little differently, and I also just want to explain what I mean by that particular answer. 72 million meters, I'm going to write in scientific notation as 7,2 times 10 to the 7 meters. Now, 72 times 10 to the 6, or 7,2 times 10 to the 7. I hope you can see we've divided the 1 by 10 and multiplied the exponent by 10 to give us 1 decimal place, and that gives us the correct answer. Now, guys, there's just one thing that's bothering me. This is the distance that the signal has traveled. But the question, if we go back, was how high above the Earth. Now notice what I did over here. I said that it went up and it came down. So we've got the distance for going up and down. So I'm wanting to remind us that this is up and down. But what we really want is to get height. So be careful when you read the question. What you need to recognize is that height is going to be half times the distance that the light has traveled, and that gives you this very impressive number there. We've got to divide by 2, and we're going to get an answer equal to something like 3,6 times 10 to the 7 meters. Okay, that is huge. That's the height above the Earth. It's hundreds, or if we even divide it by 1,000 to get it into kilometers, and we can do that, that would give us 3,6 times 10 to the 4 kilometers. Okay, so it's telling us it's about 36 kilometers, 36,000 kilometers above the Earth. That's a huge amount. So you've really got to know your stuff and recognize this is where those satellites are that in geostationary orbit above the Earth. And that's about right. Very good. Let's move on. Now, the next question says, what is the wavelength of the light emitted? Now, wavelength, we're going to need to use this information. 4,04 times 10 to the 14 hertz. So we want to get wavelength. Now remember, for number B, let's write down our original formula. And that said that C, the speed of light, is equal to the frequency times the wavelength. So we substitute in again, 3 times 10 to the 8 meters per second. The frequency was 4,4 times 10 to the, let's just make sure that I don't get it wrong, times 10 to the 14, times 10 to the 14 hertz, times the wavelength. Now, there again, you can change the subject to the formula and say, therefore, that the wavelength is 3 times 10 to the 8 divided by 4,4 times 10 to the 14. And remember, this is going to give you an answer in meters. Okay, so let's get it up and let's clear our calculator. We're going to go 3 exponent 8 divided by 4,4 exponent 14. And we get an answer in terms of a decimal of 6,81, rounded off to 6,82 times 10 to the minus 7 meters. So let me just move that so I can get my pen. 6,82 times 10 to the minus 7. 6,82 times 10 to the minus 7, and my answer is in meters. Okay, so guys, I hope you can start to see that there is a relationship here that is a very important one, that you can take note of it and that you can manipulate it. Let's move on to question C, which was really quite interesting, and says, if a different high frequency laser was used, would there be a difference in time? Well, now, what we've got to recognize here is that light, visible light, is part of the electromagnetic spectrum. And all light that is part of that electromagnetic spectrum travels at the same speed. The speed is constant. C is 3 times 10 to the 8 meters per second. So even if I increase the frequency, I'm not going to increase the speed. The speed will stay the same. So the answer to this is no. It will remain the same. The only possibility of using a different frequency laser beam is that it might be able to have more energy in it, but that's another story. In terms of the time, it won't take any longer. It will be able to travel the same distance in the same time, have the same speed, because we're talking about the speed of light. Nothing can travel faster, or light can't change its speed. Every frequency of light travels at the same speed. Be aware of that. Okay, so last thing. If we needed a slightly longer time to measure, now 0,24 seconds is quite a short period of time. Although there are clocks that can measure a lot more accurately than that, maybe I'd like to have a slightly longer time to measure. What's one of the ways I could do it? Well, there are different things that we could suggest, and I suppose we could possibly measure all sorts of different things, but here's an idea. If we, instead of allowing the beam of light to travel vertically upwards, so instead of placing my mirror over here and letting my laser go from this position directly up, what I could do is I could move off to the side, and I could now allow the laser beam to travel at an angle. The angle here is going to be critically important though, because remember, if this is a mirror, it's going to need to strike the mirror and it's going to need to obey the laws of reflection. So wherever it strikes the mirror, then we recognize that we could have a normal to that mirror. The beam of light will strike the mirror, and whatever the angle of incidence is, if that's the angle of incidence, then the angle of reflection is going to be the same. And that's the angle of reflection there. This means that the beam of light will then travel somewhere down here. It won't come back to the same position. And I'm sure you can see just by drawing that this side that we originally measured, this up and down direct distance, is going to be a lot shorter than if we did an angled direction, taking it along the pink line that I'm just drawing there. And because it's moving in that direction, we'd be able to measure exactly the time. The time would take a little bit longer. Now, bear in mind that there are some other factors to consider. One being that the Earth isn't a smooth, flat surface. The Earth is spherical, which has a curvature to it. So this calculation would be just an approximation. Although there is maths that will allow us to do it, and in fact, when they're testing lasers and they're testing distances, they can do that over the Earth, not necessarily make it straight up and down. Okay, so we've dealt now with two ideas. The first idea is speed and the speed of light, and we've also dealt with reflection. The next idea we're going to deal with is the idea of refraction of light. Now, there is an important law that we're going to use here. It's Snell's law. You need to know Snell's law and you need to be able to manipulate it. In fact, this is going to be the thing that we'll focus on for the majority of our calculations today. So make sure you're familiar with it and you've got all the concepts buttoned up, but let's just revise it very quickly so that we're very clear about it. Remember, the first part is like the law of reflection, which says that when light travels from a material with refractive index N1 into a material refractive index N2, the refracted ray, the incident ray, and the normal to the interface between the materials all lie in the same plane. And we've said that for the law of reflection as well. The incident ray, the normal, and the reflected ray, when we're talking about reflection, all lie in the same plane. So we're saying the same thing. But the second part of Snell's law is the calculation bit, and that's the part that we want to focus on today. It says the angle of refraction, theta r, is related to the angle of incidence, theta I, by this equation. And it's not a difficult equation. It simply says N1, and remember N1 is the refractive index of material 1, and N2 is the refractive index of material 2. Now we're going to be able to have a relationship between the refractive indices and the angles of incidence and the angle of refraction. We've gone over in our previous session to make sure you understand how the light is going to change, whether it's going to speed up or it's going to slow down, whether it's going to change its angle as well. You need to bear those all in mind. Just don't blindly use the equations. Make sure you're thinking about them as you go about it. Right, let's get into our first example, it's question number 2 that deals with refraction. So it says the following: a ray of light, beam of light, moves from air into a transparent glass block. So the light is going to move through it. Remember, that's the word transparent, means that the light isn't going to be reflected off its surface. It's going to pass through. They give you the diagram there, the glass block, air on the outside. It then gives you the beam of light indicated in green, and they've drawn in the normal for us. Now, I want to highlight here, the first question says to us, what is the value of the angle of incidence? Incidence means coming in. So incidence is this one here where the light is striking the block on the outside. It's moving from glass into air, and we can simply write that down. The angle of incidence here is 59 degrees. Remember, it's measured from the normal. So as I've indicated it here, it's measured from the normal to the incident ray. This is the incident ray, and we're recognizing it's going in. Now, the second question tells us is to write down the angle of refraction. Well, here we need to be very clear. When it's moving from air into glass, we recognize it is slowing down. So the beam bends towards the normal. The refractive index, the index of glass, is bigger than the refractive index of air. Air, refractive index about 1, glass, quite a bit bigger. So we'd expect it to slow down. What we've got to remember here is that the angle is going to decrease because it's always measured between the normal and the refracted ray. So what we need to look at very carefully here, it's not this angle. It's not 55. Certainly not. No, it's the angle between the ray and the normal. So we recognize that a normal is a line that strikes the surface. Just remember, a normal is perpendicular to the surface. In other words, it makes an angle of 90 degrees. So if we want to find the angle of refraction here, what we're going to do is we're going to subtract 55 from 90. So to get the angle of refraction, and I'm going to call it theta r, we're going to say, well, it's 90 degrees minus 55. Now, if you recognize that very easy calculation, it's going to be 35 degrees. Make sure you've got it. If you're not sure about the arithmetic in your head, use a calculator and check it, but I'm not going to do that right at the moment. So what we've got so far is the angle of incidence, and we've got the angle of refraction. It now tells me to calculate the refractive index of the block. So here I'm going to use Snell's law. So what do we recognize? We recognize that we've got Ni times sine theta, this is for number C, sine theta I is equal to N R, or 2, this is the second one, the second material, times sine theta r. So in fact, if I wanted to be really correct here, what I would do is not just do any arbitrary thing there. I want to make it clear what I'm doing. I'm going to put a G for glass, and I'm going to put an A for air. Could even write in the word air there. So what's the refractive index of air? Well, we know, let's just list our variables here. For air, we know it's 1, 0, 0. For glass, we don't know. That's what we've got to try and find. For the incident angle, the angle of incident, we just read it off the point here. It's 59 degrees. So 59 degrees. And the angle of refraction was 35, because we subtracted from 90 to get the 35. So if I'm wanting to get the answers now, all I've got to do is substitute those values in. And so I'm going to say 1, 0 multiplied by sine, the angle of incidence, 59 degrees, is equal to the refractive index of glass times the sine of the angle of refraction, which was 35 degrees. So there I go. And what does that tell me? To get my refractive index of glass, this particular glass, not all glass is the same, we're going to take 1, 0 times sine of 59 degrees, and we're going to divide it by the sine of 35 degrees. So let's put all of that onto the calculator and see what answer we get. See if it's reasonable. So clear the calculator. We're going to say 1 times 59, sine 59. I'm not even going to worry about putting the 1 in. I'm just going to say sine of 59. Then I'm going to divide that by the sine of 35. Close the bracket and say, give me an answer. And it gives me 1,49. Now, that seems to be about right in terms of glass. We would hesitate if it had been 2 or something like that. We know that diamond is up in the 2s, but if it had been 0, something, we'd also be a little bit concerned. Couldn't be 0. It has to be bigger than 1. So we're quite happy that it's 1,49. Rounding off to 2 decimal places there, say refractive index of glass 1,49. Great. Let's move on. So it now tells me calculate the speed of light through the glass block. Now, remember what we've said is the refractive index of glass is going to be the ratio between the speed of light and the speed of light through the velocity through the block. So what we recognize here, it's the speed of light divided by the velocity. We're going to say to ourselves, we want to get the V. And let's substitute in our different values, and we can do that quite straightforward. 1,49 is equal to 3,0, not 3,8, 3,0 times 10 to the 8 divided by V. So where does that leave us? We're going to say, therefore, V is equal to 3,0 times 10 to the 8 divided by 1,49. So it's changed quite a bit. We're going to divide by 1,49, it's almost 1.5, 3 exponent 8. Do your rounding off. Don't want to get extra places. Divide by 1,49, and there we go. We're going to say that the speed of light here is 2, and then you can count the number of zeros, 1, 2, or the number of digits after the 2. 1, 2, 3, 4, 5, 6, 7, 8. So it's 2,0 and rounded off to 1 decimal place or even 2 decimal place, 2,0 times 10 to the 8. Let me write that down so we've got it. 2,01 times 10 to the 8 meters per second. So it's got quite a bit slower. Light isn't traveling as fast as it was previously because it's gone from air, where there's nothing stopping it from moving, to glass, where there's a material that hinders the motion of light through it. So we've got that one sorted, and I hope you can see that this isn't taking us too long to get through. But let's have a look at the next one. It says the beam of light enters a different rectangular block. Important that it's a different rectangular with the same angle of incidence. So the angle of incidence isn't different. The second block is made from a material which has a higher refractive index. Okay, so it has a higher refractive index. We'll bear that in mind. how does the angle of refraction in the second block compare to the angle of refraction in the first block? So, very important little calculation that we've got to do. What we recognize is that the angle of incidence is, let's just make sure that we've got it, the angle of incidence was the same, and that angle of incidence was 59 degrees, just like what we've drawn up above. What we've told is that the angle of the refractive index is going to be bigger. The refractive index of the second material is going to be bigger, so it's going to be bigger than 1,4. It's going to be greater than 1,49. Okay? And what we therefore can say is two things. We want to recognize what's going to happen to the angle of refraction. That's the question. Let's have a look at our Snell's law equation. And where we go with Snell's law is to say, right, we start with n for 1 times sine theta. So that's all the same. Now we're going to make this value for the second material, and we're going to say that's the angle of refraction. This is the angle of incidence. That's the angle of refraction. So this part of the equation is exactly what it was previously. It's going from air into the new material. But guys, what we're saying is now is we're dividing by a bigger number. Okay? So if we're dividing by a bigger number, this number has increased. This number has got bigger. So sine of theta, the new sine of theta, is going to be smaller. We've got a constant, n1 sine theta 1, and now we're going to put n2 over here. This is going to make it bigger. This is bigger, which means that the equation, the fraction, the ratio is going to get smaller. If the ratio gets smaller, what we recognize is that if you recognize from the sine graph, sine of 0 is 0. So the smaller the number, the smaller the ratio, the smaller the angle. So therefore, we're going to say that the angle of refraction is going to be smaller. Now, does that make sense? Let's have a quick look at it in terms of what we know. We recognize, first of all, that if we've got a block over there, and we recognize we're going from air into a medium, and we recognize that there's the normal, and this is a more dense medium. Then there's going to be optically more dense, high refractive in, more refraction. It's going to bend towards the normal. And if it is more than it was before, then it's going to make this angle smaller. So angle theta r is smaller because this medium was optically more dense. R is bigger. The second one, or the second material, is bigger. The refractive index is bigger, so you're going to get more bending. It's going to slow down more, so the angle theta is going to be smaller. I hope that makes sense. We've done it from a mathematical point of view, as well as looking at the fact that when an object slows down, it's going to be refracted more. It's going to bend towards the normal more because it's slowing down more. Okay, guys, you know what? I think we've earned a break. Hope you've followed so far. When we come back, we'll be doing some more calculations on this very important topic of refraction. See you after the break. Welcome back, guys. I hope you've had a little stretch and you're ready to start with the next question. Let's dive straight into it. And interestingly enough, it's all about diving. So here we go. Question number 3 says, first of all, the refractive index of water is 1,3. The refractive index of air for this calculation, we're going to take it as 1,003. Just getting some more accuracy on that to show that it's not exactly the same as the speed of a light in air isn't exactly the same as the speed of light in a vacuum. So it tells us that a diver, somebody goes into water, is either doing some snorkeling or is looking at fish in an aquarium or something like that, practicing, learning how to do repairs to ships or wrecks that are undersea. So this diver shines a thin beam of light through water into the glass window of the diving pool. So we'll draw a picture just to show this. The angle of incidence of the beam is 30 degrees. The angle of refraction inside the glass is 25,94 degrees. And the two questions we're asked to calculate in this context is, first of all, to find the refractive index of the glass used in the diving pool, and secondly, to calculate the angle of refraction of the emergent beam. Okay, so there's quite a mouthful there, and we need to be really careful. So when you're given a problem like this, one of the things you need to do is to draw a picture. So my drawing isn't terribly good, so I'm just going to draw a very simple sketch. I'm going to call that the window, and I'm going to magnify the window and make it quite thick so I can have a substantial sense of a window. And windows are normally have parallel sides, and so I'm going to say, here's my, first of all, let's put in the normal. And we're going to say, there's the normal over there, and let's put in a beam of light. Secondly, try and use a different color to show the beam of light. I want it to go in that way, but I'm going to just move it so it's pointing in the right direction. So it's coming from water. So it's in water to start with. The refractive index of water was given right at the top there of 1,3. We don't know the refractive index of this glass, but we know that on the other side here we've got air, and the refractive index of air here was 1,03. Okay. We also know that the incident ray, the angle of incidence, was this angle here, and is 30 degrees. Remember, it's measured from the normal. That is critical. You can't just measure it from anywhere. It's measured from the normal to the beam, as I've indicated it over here. So please make sure that you do draw a little sketch, and we're now wanting to calculate the refractive index of glass. So we're really interested in what's going to happen over here. There's another bit of information I've almost left out. There it is. The angle of refraction inside the glass is 25, almost 26 degrees. So if I use my little arrow, it's not 30, it's just going to bend slightly. It's not going to bend too much. It's about there. And I can now fill that in 25,94 degrees. 25,94 degrees, that's the angle of refraction. So I think I've got all that I need. Angle of refraction, 25,94 inside the glass. So what equation do you think we should use? We've got the angle of incidence, we've got the refractive index in water, we've got the refractive index in glass. Well, we haven't got the refractive index in glass, we've got the angle of refraction. We're wanting to find the refractive index in glass. So what equation are we going to use? Well, let's do it. I think we're just going to apply Snell's law. So remember what it is? N1 times sine theta I is equal to N2 sine theta R. And we're wanting to find this one. We're wanting to find the refractive index of glass. So here we go. We'll substitute our values in. Don't try and rearrange the equation. We'll just get a mess then. We're wanting sine of 30 degrees, which is equal to N of glass, N2 is the refractive index of glass, times the sine of this angle, 25,94 degrees. And if we now rearrange the subject of the formula before we put it on a calculator, that shouldn't be a problem. We get 1,3 times sine of 30 degrees divided by sine of 25,94 degrees. And it's all looking very good. Let's get the calculator up to confirm our calculations. So 1,3 times the sine of 30 degrees. Some of you are shouting at me and saying, 30 degrees is a special angle, it's equal to a half. Yes, I know, but just check it on the calculator. And then we're going to put sine of 25,94, close the bracket, make sure we've got that, and we get a refractive index of glass of 1,52. So 1,52, 2 decimal places, 1,52. And there we go. Just remember to say, therefore we can say the refractive index of glass, let me just rewrite that very clearly, so we can say, put it in words, the refractive index of glass, of this glass, N2, is equal to 1,52. Excellent. So the next part of the calculation, part B now, says calculate the angle of refraction of the emergent beam. So guys, here's the challenge. This beam isn't going to get stuck inside the glass. It's going to strike the surface of the glass, which is parallel to the original one, and we now need to calculate the angle of incidence. We know the refractive index, we know the refractive index of air, but let's make sure that we've got this very clear. So if I now draw in my normal, I'm going to extend my line a little bit so that you can see it. It's now going to strike that position over there. I've got another normal. Now remember, the normals are going to be parallel to each other. And hopefully what you can see is between the parallel lines that this angle and that angle, because these lines are parallel, the normals are parallel to each other, those two angles shaded in pink are going to be equal to each other. So the angle of incidence now at the second surface, the angle of incidence between when we're moving from glass to air, the angle of incidence is 25,94 degrees. That's the angle of incidence. We know that the refractive index of glass in the window is 1,52. We know that the refractive index, don't know why I was writing G there, the refractive index of air in this particular case was given as 1,003, and we want to find the angle of refraction. Now, before we get to it, guys, I need you to be thinking. It's moving from an optically more dense to an optically less dense medium. Remember, we're going to measure the angle of incidence from the normal. What do we predict? Is it going to be smaller than 25 or is it going to be bigger? I hope you can see that because it's moving from a more optically dense, a medium with a high refractive index to a low refractive index, the light is going to speed up and it's going to bend away from the normal. We're expecting the refractive index to be bigger than it was before. So in this case, the angle of refraction to be bigger than 25 degrees. The refractive indices will stay the same. So angle of refraction, we must predict is going to be bigger than 25. Let's see if it works. N1 sine theta I, N2 sine theta R. Now, we're wanting to find sine theta r on its own, but let's substitute first of all, and then we can manipulate and change. The reason we do this is so that you can get the marks. Now, the refractive index of the first material was the glass, and we calculated that as 1,52. 1,52, the angle of incidence was 25,94 degrees, and we recognize that the angle, the refractive index was given as 1,003, and then we can say sine theta for refraction. This is in air, so that we're moving, remember, from glass over here to air over here. So let's find out what sine theta r is. We're going to change the subject of the formula. 1,52 times sine of 25,94 degrees, and we're then going to divide that by 1,003. Let's see where we go. Put it into the calculator, and I need to just move the calculator across so I can clear it and then put the values in. 1,52 times the sine of 25,94, and then I'm going to divide that whole thing by 1,003. Gives me an answer of 0,663. 0,629. I'm going to round that up to 0,663. But remember, this is what sine theta is. So we now don't want to just know what sine theta is. I'm going to write it down, but we want to find the angle. So let me write this down first of all, and then we'll come back and find the angle. So we can say sine theta is equal to 0,669. 663, because it was 6,629. So I'm going to write it as 663 and leave it like that. How are we going to find the angle? Well, remember, your calculator does help you to do this. We're going to say, be careful. We're going to take the shift, and we're going to say sine, and we're going to put the answer in from our previous part, the full answer, and we get the angle of refraction being 41,52. So therefore we can say the angle of refraction 41,52. Theta, the angle of refraction, 41,52 degrees. Got it? Does it make sense? Let's go back to our diagram. Recognize that this angle of incidence was 25. We're saying the angle is 41. So it's going to sit somewhere over here. And yes, that does make sense, that it was 41,52 degrees. It's bent away from the normal. I hope you can see how we're applying Snell's law to get various answers. Okay, there is one further little section that we need to cover that has relevance to Snell's law. And I want to remind you that this is what happens, just like we've just calculated, where something is moving from an optically dense medium to an optically less dense medium. And the process is called internal reflection. So what is internal reflection? The first thing we need to recognize is that we need some conditions. Light must travel from a high refractive index, N1 greater than N2. So it's a high refractive index to a smaller refractive index, from an optically dense medium to a less dense medium. In other words, it will be changing its speed. It will be moving from slow in the first medium. It's going to be moving fast in the second medium. And then the second thing that we need to recognize is that when light does this, then if the angle of incidence is greater than something called the critical angle, then we won't get refraction, but we'll get reflection. So the critical angle, what is this critical angle? The critical angle is equal to the angle of incidence when the angle of refraction is 90 degrees. So if it's greater than that particular angle, when the refraction angle is 90 degrees, well, then you've got the critical angle. Then you're going to get reflection, internal reflection. And we showed why this is useful. It's useful in fiber optics, it's useful in binoculars, and a whole lot of other things. So in this section, though, we want to do some calculations with critical angles and make sure that we understand how we're going to get them. So let's move on to our next question. And here it is. It's really very straightforward little question that needs us to think a little bit. And here it goes. It says the refractive index of water is equal to 1,3. Now remember what that means. Refractive index is the speed of light divided by the speed of the object in that material. And the first thing that we're asked to do is to calculate the speed of light in water. We're going to use that formula. The second thing, it says calculate the critical angle of water. Now, this is with respect to air, and I'll come and explain that. Let's do the first part because I think it's quite easy, and let's make sure that we get it. So we're going to use the fact that the critical angle is equal to the speed of light divided by the velocity of the light in that medium. And we're going to say that in water it's 1,33, and the speed of light is 3 times 10 to the 8 meters per second, and we recognize that v is the speed of light in water. So we want to find v in water. We're going to change the subject of the formula after we've substituted, and we are then going to see that it's 3 times 10 to the 8 divided by 1,33, and using your calculator, you'll get that the speed of light in water is going to be a little different. 3 times 10 to the 8 divided by 1,33 equals 2,26 times 10 to the 8 meters per second. So if you count up the zeros, you'll be able to see that that gives you 2,26 times 10 to the 8. If you divide that again by 100, it will change from 10 to the 6 to 10 to the 8. And I'm going to write it like that. In the correct scientific notation, write it as 2,26 times 10 to the 8 meters per second. Let me just check that. I want to make absolutely sure that I've rounded off correctly. 2,2, the 5 makes that 5 a 6, and that's exactly it. 2,26 times 10 to the 8 meters per second. So it's quite a bit slower than the speed of light in air or in a vacuum. We've decreased quite substantially in water. But now the next thing is the critical angle. How are we going to get this critical angle? Well, remember, the critical angle is when we go from, here's the diagram that you need to really take note of. If that's the interface between water on this side, we always travel from water into air, and I'll explain now why I'm using air as the standard. We're going to say the refractive index is 1,33. The refractive index in air we're going to take as 1,0. Now, what we're saying here is that the speed of light is 3 times 10 to the 8 meters per second. It's going slower in the water. It can never go faster than the speed of light in air. That's why we've made the refractive index as 1. So that's, in a sense, going to be the critical angle for the least something that has the lowest refractive index possible. So in this sense, anything else will have that we put in its place, we'll see, has a different critical angle, but this one is the critical angle with respect to air. So where are we going to find? We want to know what is the size of the angle of incidence. We want to get the size of the angle of incidence. Let me redo that because I drew it the wrong way. The angle of incidence when the angle of refraction is 90 degrees. So let's put the normal in so you can measure this and you can see it very clearly. This is going to be known as the critical angle. And the reason it's critical is because if we had an angle bigger than this, then it will be total internal reflection. The angle of refraction here, the angle of refraction is 90. That's this angle here. So that's what we're trying to establish. And I hope you can see that that's nothing more than a Snell's law calculation. So we're going to say we want to find sine theta incident when the angle of refraction for air is going to be 90 degrees. Now, what's the sine of 90? Sine of 90 is 1, and the refractive index is 1. So what you recognize here is the refractive index of water was 1,33, and this is the sine of theta, I, and we're wanting sine of theta on its own, so we're going to say it's 1 over 1,33, and we will then be able to plug that into the calculator. Right, let's put in 1,33. Now, if you've got a number like this to 2 decimal places and you want to use it as a denominator, here's a quick cut, a shortcut to help you do this sort of calculation. Instead of writing in anything else, if that was on your calculator, go to this reciprocal button, and if you now push the answer, it will give it to you as a decimal number spewed out there. You could obviously then, if this was part of a bigger calculation, multiply by the numerator and so on. But in our case, what we need to do is we now need to recognize that sine theta of the incident angle, sine of the incident angle, is going to be 0,75187. But I want to find theta I. I want to find the angle of incidence. So how am I going to do that? I'm going to take shift, and I'm going to say sine, want the reciprocal of sine or the inverse function of sine, and I'm going to put my answer value here. So I'm going to put in the ratio that I've just found out, and I'm now going to be given the angle. And so I can say that my angle is theta is equal to 48,75. 48,75. Let me write that down. Theta I, 48,75 degrees. So, guys, remember what this means. This is the critical angle. The critical angle for water, when light is changing from water to air, then the critical angle for water with respect to air is 48,75 degrees. What does that mean? Well, let's just do a couple of drawings so that you've got it very clear. If I have my interface here, and if I have water on the left, and I have air on the right, and I'm going to put in a couple of normals here, just to give you the 3 cases. That one doesn't look very much at 90 degrees, so let me just straighten it, and let me put in another one down here, and a third one a little bit further down. I'll just extend this line so that we can get a third one in as well, and I need you to follow very carefully. If this is a normal, then it needs to look a bit like a normal. So, first thing is what we recognize. If the angle of incidence the angle of incidence is less than that critical angle. Look at the critical angle again, 48. So this angle here, the angle theta, is clearly smaller than the critical angle. It's less than the critical angle. It's a small one. What are we going to get? We're going to get refraction. It's moving from water into air. That means it's going to speed up when it leaves the water, and it's going to bend away from the normal, something like that. The angle of refraction on this side is going to be bigger than the angle of incidence. That's going to be the angle of refraction when we're moving from water to air. Now, if it was equal to the critical angle, we've already shown this case here. If the angle of incidence in the water is equal to the critical angle, then what are we going to get? Well, it's not difficult to see. We're going to get that the angle of refraction is going to be 90 degrees. So if it was that 48,75 angle of incidence measured from the normal, and we recognize that this angle here is the critical angle. If that's equal to the critical angle, then we're going to get an angle of refraction that is equal to 90 degrees. And the last scenario is what happens if my angle of incidence is greater than the critical angle. Well, you need to be very clear about this. If it's going to be greater than the critical angle, then we're going to get internal reflection. So I need to draw it very carefully, and I'm going to be very clear that this angle must be bigger, must be a big angle. So if this one was, say, 60 degrees, then this is going to be 60. It's going to reflect internally. Even though we're going from water to air, we recognize most times light is going to pass from water to air. Water is a transparent material. But if the angle of incidence at the surface, at the boundary, is not is bigger than the critical angle, bigger than 48,25 degrees, then we're going to find 75 degrees. Then we're going to find that there's internal reflection. So if you're ever in a swimming pool and you look up at the air, the air above you, and you look at an angle, you might be able to see some strange images because of the way light is traveling inside the water and it's being reflected back to you. So there's something of interest. Now, there's one last part to this question that I think is very interesting. The critical angle, you've noticed I've said the critical angle with respect to air. It's with respect to a boundary. And here is my next part of the question. It says, if the beam of light strikes the surface of water and glass, okay, so it's not water only and water and air anymore, but if a beam of light strikes the surface of water and glass where the refractive index of glass is 1,42 at an angle of 52 degrees, will total internal reflection take place or not? Well, guys, here, this is an interesting dilemma, because what we recognize is that the critical angle for water with respect to air is, we worked it out, it was 48,75. Look over here, there it was, we just worked it out, 48,75. So what we would say, 48,75 degrees. We know that's the critical angle, and we know that this angle of incidence now is 52 degrees, which is greater, the angle of incidence is greater than the critical angle, but that was with respect to air. So the question now is, if we are going from water on this side, water, and we're going into glass, not into air. The refractive index of water, remember, was given as 1,33, and the refractive index, there we've got it, 1,33. The refractive index of glass was, of this particular glass, was 1,42. So the refractive index, 1,42. Now the question is there still going to be total internal reflection? Well, guys, there are a number of ways of solving this. But the easiest way is simply to apply Snell's law and say to ourselves, if the angle of incidence is 52 degrees, let's apply Snell's law. We're going to say N1 sine theta I is equal to N2 sine theta 2. Sorry, that shouldn't be 2, but should be an R. Let's see what we're expecting. Now, if we substitute in, we get 1,33. That was for the water. The angle was sine of 52 degrees. We're going to get N2 here as being 1,42. And we want to know the angle of refraction. So we just simply rearrange, and we're going to get sine theta R is equal to 1,33 times sine of 52 degrees divided by 1,42. Now, I hope you can see something here without even going further on the calculator, that the ratio of these numbers is going to be smaller. That's going to give you a number that is smaller than 0, smaller than 1. 1,33 divided by 1,42 is going to give you a fraction. A fraction times the sine of 52 is going to give you a smaller number. So we're predicting that the angle should be smaller than 52. And we'll have a look and see how we can apply that and make sure that we've got it right. So let's just check exactly what is going to happen. Sometimes our predictions don't work out, but let's particularly take this one and let's see how we go. Let's substitute in 1,33 multiplied by the sine of 52, close the brackets, divided by 1,42, and that's going to give me an answer of 0,738. Okay, I'm going to round that off to, or just going to use the shift function on that to get my angle, because that's really what I'm wanting. But I do want to take a note of it, so I'm going to write it down, 0,738. Sine of theta r, 0,738. Now, let's get the theta, the reflected angle in here. Let's use our shift function. Shift of sine, give the answer, and we'll get 47,56 or 57. 47,57. So let me write that in. The angle 47,57 equals 47,57 degrees. Now, guys, remember what we said here. The angle of incidence was 52. The angle of refraction we've worked out as 47. But remember what we're doing. We're working from water to glass. Is this surprising? Well, you should have recognized that because we're going from water to glass, we're going from where there is a low optical density to a high optical density. You're never going to get total internal reflection. What's going to happen is, because you're going from a low refractive index to a high refractive index, what's going to happen? The light is slowing down, so it's bending towards the normal. So we could have answered that very simply and said, no, we're going from a low refractive index to a high refractive index, no internal reflection. But I wanted you to see that you can calculate the angle of refraction. You now have to interpret that and say, oh, what does that mean? There's the normal, and if I had my angle of 50 coming in over here, it was 52 degrees coming in at this particular position here, and I'm now only getting an angle of 47. Well, remember that's also measured from the normal. I'm going to see that it's bending towards the normal, and certainly this is not going to be internal reflection, 47,57. There's no way that that's going to produce internal reflection. Okay, remember the conditions. Don't fall for the trap. But remember as well, the critical angle is dependent on the media. So it's not always going to be 50, whatever it was. It's not always going to be, we calculated the critical angle earlier as 48,75. What happens if we had water to another substance? Well, there's something for you to perhaps go and have a look at and see if the critical angle will change. I think it will. You do an investigation. Well, it's been my pleasure being with you. I hope you've enjoyed this. I hope it's helped you consolidate all you need to know about light, and all the best for your tests and exams. From me, John, goodbye.